In this video, we will have a look at the monostable multivibrator circuit, its construction, operation, and related parameters. The basic transistor circuit for an Astable multivibrator produces a square wave output from a pair of grounded emitter cross-coupled transistors. Both transistors, either NPN or PNP, in the multivibrator are biased for linear operation and are operated as common emitter amplifiers with 100% positive feedback. When power is applied, theoretically both T1 and T2 should turn on, since their base pins are connected through resistors R2 and R3 to VCC. However, due to small differences in the electric properties, one of them will turn on slightly earlier than the other. Without loss of generality, let's assume T2 turns on first. Plate A of capacitor C1 is also rising towards the plus 6 volt supply rail of VCC, as it is connected to the collector of TR1, which is now cut off. Since TR1 is in cutoff, it conducts no current, so there is no volt drop across load resistor R1. The other side of capacitor C1, plate B, is connected to the base terminal of transistor TR2 and at 0.6 volts because transistor TR2 is conducting saturation. Therefore, capacitor C1 has a potential difference of positive 5.4 volts across its plates, 6.0 volts and 0.6 V volts, from point A to point B. Since TR2 is fully on, capacitor C2 starts to charge up through resistor R2 towards VCC. When the voltage across capacitor C2 rises to more than 0.6 volts, it biases transistor TR1 into conduction and into saturation. The instant that transistor TR1 switches on, plate A of the capacitor, which was originally at VCC potential, immediately falls to 0.6 volts. This rapid fall of voltage on plate A causes an equal and instantaneous fall in voltage on plate B. Therefore, plate B of C1 is pulled down to negative 5.4 volts, a reverse charge, and this negative voltage swing is applied the base of TR2, turning it hard off. One unstable state. Transistor TR2 is driven into cutoff, so capacitor C1 now begins to charge in the opposite direction via resistor R3, which is also connected to the positive 6 volt supply rail, VCC. Thus the base of transistor TR2 is now moving upwards in a positive direction towards VCC with a time constant equal to the C1x R3 combination. However, it never reaches the value of VCC, because as soon as it gets to 0.6 volts positive, transistor TR2 turns fully on into saturation. This action starts the whole process over again, but now with capacitor C2 taking the base of transistor TR1 to negative 5.4 volts, while charging up via resistor R2 and entering the second unstable state. Then we can see that the circuit alternates between one unstable state in which transistor T1 is off and transistor T2 is on, and a second unstable in which T1 is on and T2 is off at a rate determined by the RC values. This process will repeat itself over and over again as long as the supply voltage is present. The amplitude of the output waveform is approximately the same as the supply voltage, VCC, with the time period of each switching state determined by the time constant of the RC networks connected across the base terminals of the transistors. As the transistors are switching both on and off, the output at either collector will be a square wave with slightly rounded corners because of the current which charges the capacitors. This could be corrected by using more components, as we will discuss later. If the two time constants produced by C2x R2 and C1x R3 in the base circuits are the same, the mark-to-space ratio will be equal to 1:1, making the output waveform symmetrical in shape. By varying the capacitors C1, C2 or the resistors R2, R3, the mark-to-space ratio and therefore the frequency can be altered. This is known as the pulse repetition frequency. So Astable multivibrators can produce two very short square wave output waveforms from each transistor, or a much longer rectangular shaped output, either symmetrical or non-symmetrical depending upon the time constant of the RC network.